All right, this is lesson 7.4, similarity in right triangles. We're going to learn how to find and use relationships in similar right triangles. Yeah, I just want you to think about this for a moment. It'll help you think about the concepts that we're learning. If 3, comma x, comma 12 is an arithmetic sequence, what is x? So the word arithmetic means that we're adding the same amount. There's a constant difference. So that means that if I do x minus 3, it will equal 12 minus x. And so, so basically what I'm looking for is a number exactly halfway between 3 and 12. And one way I can find that is by finding the arithmetic mean. Which is just saying I can just add 3 plus 12, which is 15, and then I can divide by 2. And I think if we solve this, we'll see that it's the same thing. If I add x to both sides, then I'll get 2x minus 3 equals 12. And 2x is equal to 12 plus 3, which is 15. And then x is equal to 7.5. So x can be replaced by 7.5 if this is an arithmetic sequence. We would be adding 4.5 each time. Now think about this. If 3, comma x, comma 12, dot, dot, dot is a geometric sequence, what is x? So now I'm talking about a different thing here. I'm saying that there's a common multiple here, not a common difference. So there's some number I multiply 3 by to get x, and then I multiply that same number times 12. So what I'm saying here is if I take x divided by 3, that will equal 12 divided by x. And so what I get is this. X squared is equal to 3 times 12. Using the cross products property. And x squared is equal to 36. So x is equal to, I know it's a positive number, so I don't care that there's a negative possibility here. But we want the positive square root of 36, which is 6. So if this is a geometric sequence, then x is equal to 6. And I can see that I'm multiplying by 2. 3 times 2 is 6, 6 times 2 is 12, and so on. Well, the second idea, what we found here, we also found a number somewhat halfway between 3 and 12, but in a multiplicative way. And we called that the geometric mean. And the geometric mean is a big concept that we're going to be using in this lesson. So, all right, go ahead and whip through this vocabulary here, especially read the vocabulary geometric mean carefully so you get a good idea what that is. I'm going to pause here. All right, so an important concept here, the geometric mean is the value such that 4 divided by x equals x divided by 10. Another way we can always say that is the geometric mean is the square root of whatever my two numbers are. So we'll say a times b. All right. Which proportion can you use to find the geometric mean of 5 and 15? That would be this one here, because we get x squared equals 5 times 15, which is 75. So x equals the square root of 75. And we could simplify that. So underline the correct statement. That would be that one. So the geometric mean of 3 and 7 is the square root of 21. Circle the geometric mean of the square root of 3 and the square root of 3. That would be, think about that for a second. What we're saying is this, x over the square root of 3 equals square root of 3 over x. And we get x squared equals square root of 3 times square root of 3 is 3. So if x squared equals 3, then x equals the square root of 3. But that totally makes sense since we'd be multiplying by 1 to get from square root of 3 to the square root of 3. So, all right. Here's some concepts that we can use this idea of geometric mean with. The altitude to the hypotenuse of a right triangle divides a triangle into two triangles that are similar to the original triangle and to each other. So when you put the altitude into a right triangle like they've done here, from the right angle to the opposite side to the hypotenuse, you get 3 congruent triangles. Not congruent, but similar triangles. So all 3 of these are similar. They all have the same corresponding angles. All right, so and a corollary to that is the length of the altitude and the hypotenuse of a right triangle is the geometric mean of the lengths of the segments of the hypotenuse. And that comes from the fact that if things are similar, then the ratio of corresponding sides are equal. So what we're saying is this little segment here to this, I'll do this in green, to this green one, is equal to the green one to the other part of that hypotenuse. All right, and also corollary 2 to 7.3, the altitude of the hypotenuse of a right triangle separates the hypotenuse so that the length of each leg of the triangle is the geometric mean of the length of the hypotenuse and the length of the segment of the hypotenuse adjacent to the leg. So if we look at this little triangle here, the hypotenuse of this little triangle is AC, and that AC is the geometric mean of AB and AD. So in other words, of the whole hypotenuse of the big triangle, the whole thing, to the little part that touches that hypotenuse on that little triangle. So AB, that's right here, to AD. Okay? And similarly, the hypotenuse of the medium-sized triangle, the green line, is the geometric mean of this length and the whole length of that hypotenuse. All right? So those are the ideas we're going to use here. So let's see if we can't figure out what all the similar triangles here are. So LMN is similar to, let's break them up. Let's just show the little one here. And then the medium-sized one. And then we'll label them so we kind of know which are which. So this is the whole triangle, the last one. And if I label them using the right angles, then this one would be M and L there. This one would be N, P, and L there. And the little one would be M, P, and N. So my similar triangles are the L, the big one is similar to the medium one. That's the one I just did. The big one is similar to the small one. And then the medium one is similar to the small one. All right. Use the triangle at right. Right corollary 1 or corollary 2 for each proportion. Here's how I remember it. Corollary 1 relates the altitude to the two segments it divides. So M is the geometric mean of X and Y. That's corollary 1. Corollary 2 is where you have the hypotenuse of each of those smaller triangles is the geometric mean of the leg from the hypotenuse of the big triangle to the length of the whole hypotenuse, the adjacent part of that. So, and then this hypotenuse B is the geometric mean of this length here and the whole triangle. That's corollary 2. So let's see which one we have. So C over A is equal to a over x, we're talking about one of the hypotenuse of the little triangle, so that's corollary 2. Okay, x over m equals m over y. We're talking about the altitude. That'd be corollary 1. And the last one, we're talking about this hypotenuse from the medius side triangle. So that's corollary 2. All right, let's use some of these corollaries. What similarity statement can you write relating the 3 triangles in this diagram? Again, I think it helps to just split them up. There's 3 triangles. There's a small, a medium, and a large. And then label them so that you get all the angles in the right place. So starting here, we have EGA for the small one. For the medium-sized one, we have AGK. And for the large one, we have EAK. And then you can choose a consistent way to show each of those, but I would say something like, I'm just going to name the angle in order. So we can say triangle EGA, and similar to triangle, I'm going the smallest one to the medium-sized one, AGK. Now I'll go the small one to the largest one, EAK. Then I'll do the medium one to put similar signs in each of those, to the large one, and I got them. All right, but I'm going to pause here and you can try that. All right, here's what you should have for that. So now just finding the geometric mean. Remember, the geometric mean is the square root. So let's say x is our geometric mean. That's the square root of the 2 numbers that surround it, multiply. So for the geometric mean of 5 and 12, we'll call it x. It is just the square root of 5 times 12. And that comes from this. Remember that the geometric mean will be proportional to the smaller number and the larger number. And also remember when we talked about the means and the extremes. So this is where that term comes from. So x squared is equal to 60, and we want a positive square root, so we say x is equal to the square root of 60. And we can simplify that. 60 has a perfect square factor of 4, and the square root of 4 is 2. So 2 times the square root of 15 is the geometric mean of 5 and 12. All right, you can try that. Here's what you should have. Okay. And one more problem. We're going to use a geometric mean to help us solve this problem. I think I'll pause here. We're going to have a part 2 of this video. So check out part 2 for the rest of it.